Good afternoon, everyone, and welcome to our first Sci-Fi series event for 2021. I'm Professor Emma Johnston, Dean of Science at the University of New South Wales, and I'm pleased to be hosting today's webinar on climate extremes. We'll be asking questions such as, what are climate extremes and why are they happening so frequently? Why, when the world's heading for only a 2-degree average temperature rise, we should be at all worried. So a bit of basic explanation, but we'll also be delving deep into the modelling and the new data required and the new approaches to understanding extreme weather and climate events. And we're able to do that because our panel is a panel of experts, leading experts in their fields, and they'll share their knowledge, the latest research, some of which isn't even published yet, about extreme events, about the processes that trigger them, about the ways that they might combine to have greater impacts than just as independent events, and how we're building this understanding into modelling and forecasts. So it will be a really, really interesting session. I'm also happy to take questions from the floor. They'll come up to me via the chat, and I'll try and introduce as many questions as I can into the conversation with our experts. But before I begin, I would like to acknowledge the Indigenous lands on which we meet and the people who are the traditional custodians of those lands. I'm on Bedegal land, and many of you will be joining us from many different Indigenous land and sea countries across Australia. So I acknowledge their elders, past and present, on behalf of all of us. I pay my respect to Aboriginal and Torres Strait Islanders who are joining us today, and I acknowledge and pay my deep respect to the continuing connections to country of Indigenous people and the deep knowledge that emanates from those continuing connections. So for those who might be new to the Sci-Fi series, it's a very special event. It's a unique product of the science faculty. It's really designed to allow everybody to engage with our leading researchers to showcase the really important role of science in understanding the world and creating a better future. So we do have people who are working at the university featured in each of our Sci-Fi events. Last year we delivered the events digitally, and it worked really well. So we've kept that approach this year. It enabled many, many more people to join us online. Thank you for joining us today, wherever you're joining us from. The webinar itself, it is recorded and it's made public following the session. So if you have friends or colleagues who'd like to get involved and to understand extreme events better, then you can send that link out to those. It will be sent to everybody who's registered for this event. Before we dive in, let me introduce the panel that we have. Professor Andy Pitman, AO, is Director of the Australian Research Council Centre of Excellence for Climate Extremes. Andy's a professor in climate science at UNSW Sydney, and he has 35 years of experience and broad interests that extend across climate modelling, climate change and climate extremes. And Andy's been a lead author of the Intergovernmental Panel on Climate Change, the IPCC, as you may know it, contributing to the award of the Nobel Peace Prize to the IPCC in 2007. He has had and continues to have multiple senior advisory roles in climate science for the federal government, the New South Wales state government, as well as senior national roles in e-research infrastructure strategy, the underpinning capability that we need in order to do the modelling of climate and climate extremes. Another panel member, Professor Moninya Roughen, is a Professor of Physical Oceanography in the School of Mathematics and Statistics here at UNSW Sydney. She has expertise in the dynamics of coastal ocean circulation, so research focusing on improving our understanding of the East Australian Current, which you may know from Finding Nemo, cross-shelf exchange, coastal ocean circulation, upwelling, marine heat waves, of course, and the biological implications of all those events. She uses a lot of actual observations, but also modelling as well. And over the past decade, Moninya has been instrumental in the design and the deployment and the ongoing development of one of the most comprehensive ocean observing systems in the world, the IMOS system, which is the Australia's integrated marine observing system. She's built a vast ocean observational data sets. She flies aeroplanes underwater, basically, to do part of that. And these data sets are critical to us understanding ocean processes. Final panel member, really pleased to welcome Dr. Nina Ritter. She's joined the Australian Research Centre of Excellence for Climate Extremes in the beginning of 2019. And before that, she was working as a research fellow in the Netherlands at the Royal Netherlands Meteorological Institute and the European Space Agency. Nina's current work focuses on compound climate and weather extremes and extreme precipitation. So we are talking about when extreme weather events happen at the same time or consecutively or impact the influence of each other. So that's a really fascinating area of cutting edge research. Nina's work addresses those co-occurrences of multiple natural hazards, and they've been associated with the most severe socioeconomic damages. So she's investigating multivariate hazards on a global scale and trying to map different regions and where those natural hazards might coincide. So interestingly, both Nina and Moninya are proud alumna of UNSW Sydney, and so welcome again to all of the alumni and alumna that are watching with us today. Thank you for being here, Andy, Moninya and Nina. After that long introduction, I have to get straight into it. So I'm going to go straight to the core question that everyone must be asking themselves. You know, Australia's environment has evolved in response to many extreme events: cyclones, bushfires, hailstorms, floods, storm surges, heat waves. So when you're living in such a wild country, the first question we need to ask is, what are extreme climate events, and why are they such a hot topic at the moment? And I make no apologies for that pun. Andy, I'm going to throw to you first.
Thanks, Emma, and I think that pun is unforgivable, but anyway. So climate extremes, it really depends on what you're talking about and what system you're interested in. So a climate extreme is a very different thing in the context of drought, which might take, in Australia's context, years to evolve to be extreme, in contrast to a hail event, which might occur in a matter of seconds. And many people listening will know, I think it's still the case, that the most expensive insured event in Australia's history was a 15-minute hailstorm that hit the eastern suburbs of Sydney. So climate extremes can be very localized and short-term, or can cover the majority of Southeast Australia and last for many years in the case of drought. And in fact, in the case of some extremes like drought, we don't even know how bad they can get. There's evidence from the paleoclimate community that the sorts of droughts we might have observed in the last couple of decades really weren't very bad, which opens up real issues in terms of water resources. So a climate extreme depends, really, it becomes extreme either statistically when it's very rare, or when it hurts something important, whether it's an ecosystem or damages a building or floods a region of someone's interest. So it's difficult to talk in general terms about climate extremes. What one wants to get down and dirty into is the detail. Which climate extreme, where is it affecting, and what systems that we care about is that extreme having an impact on? And we've started to evolve our thinking increasingly away from what you think of as single variable extremes, heavy rain or strong winds, into the areas that Nina works on compound events, where you start to see a coincident, either multiple extreme rainfall events occurring sequentially over a short period of time, or the co-occurrence of two major extreme events happening simultaneously, which can have much, much more damage than either of them operating singularly. So that's a quick snapshot on extremes.
That's great. So basically it's at the extreme events side of things in terms of intensity of the event, but it could also be because it's very, very rare as well. Or I'm going to throw to Nina now, because two things happen at once, or three or four. Can you give us some examples?
Sure. So there's quite a lot of examples actually, because there's a variety of different types of compound events. And so I'm focusing on events where multiple hazards act at the same time at the same place. So a prime example for that would be precipitation and winds. So for example, in a tropical cyclone. Another example is where you have several events occurring at the same time, but spread over a large area, like what we saw in the Black Summer. So you spread out your event, your impact, and to respond to it, you have to spread out your response teams, which makes it a lot harder to deal with. So these kind of things are what complex are. Things acting together, making it harder, making the impact more severe than what we are used from univariate events.
So many people would be familiar with a cyclone bringing lots of rain, and so that not only do you get the damage of the winds and the storm and the storm surge, but later on you may well get flooding in a similar location. I think that's a familiar model for many people. Are we beginning to see different combinations of extreme events that we probably haven't seen as frequently before as a result of climate change?
It's a very interesting question. The thing is, though, that compound event research is very new. So it has started and picked up over the past 10 years, maybe. So where it got more attention in the past 10 years. Which means that at the moment we don't even know exactly which events are important in which areas. So what have we seen? What type of events were there? So that's where the research is at the moment. So in our Nature Comms paper, for example, that was the first paper that actually looked into 27 different hazard combinations globally, using observations into where did they occur, how often did they occur. So that was one of the first papers or research outputs into this kind of thing. So we don't really know. It's too short, and also observations aren't long enough for us yet to actually get into detail of what has been changing. So it's very...
So that's a great segue to Moninya, because whilst we have Andy sitting here as one of, I guess, the leading terrestrial extreme events researchers and goes well beyond that, but we could say focuses there. We've got Nina focusing on compound events. Moninya is really interested in what's happening in the oceans, and that's where data sets are absolutely precious and scarce. Moninya, what do we know about extreme events and how do we define them in ocean environments?
Yeah, it's a really good question, Emma, and it's something that we're really only just starting to get a handle on. This is really new research. So in the ocean, we refer to warm events, extreme warm events, as marine heat waves, and very cold events as marine cold spells. Now, to know if the event is very warm or very cold, you actually have to have a long time series, which Nina just said. So when we define these events, we generally like to have a 30-year record of ocean temperature that then you can assess the anomaly against. So is this warmer or colder than the mean over 30 years? And these extreme events are in the top and bottom 10th percentile. But it's actually really hard to get 30 years of data in the ocean. We know so little about the ocean. It's so deep, 4 kilometres deep on average, so vast. So generally, the longest time series of the ocean are from satellites, so satellite data. But the satellites only measure the very surface of the ocean, at best a few centimetres or a few metres. So we only have that temperature observations at the very surface of the ocean. So we know so little about what's going on below the surface. And so we're very fortunate in Australia to have some of the longest subsurface ocean time series in the world. We're just working up a 70-year time series that, with the foresight of CSIRO, they started going out off Port Hacking off Sydney in the 1940s in a little boat, heading offshore, collecting their subsurface temperature information, sort of lining up a few trees to see if they were in the right spot every week. And they did this weekly for decades. And it is a remarkable time series. And with those data, we have it off the west coast of Australia, off Rottnest Island. We also have another time series off Maria Island. And with these data, we can see now the subsurface structure and the changes in ocean temperature, and that these marine heat waves are actually more intense at depth. So these subsurface information is really important, and they last longer at depth. And so knowing what's going on beneath the surface is really, really important.
And moving just a little bit into the biological effects or the potential biological effects, what happens if you get an enormous slug of hot water, which is unusually hot, sitting in the ocean? Do we understand what the impacts might be?
I think to some extent we're just starting to learn that. We had the Ningaloo Nino event off the west coast of Australia, off Western Australia, And during that event, I think it was back in 2011-12, we saw that all the kelp died. A lot of things died, and they've struggled to come back. So once you have this extreme event, it might be a short-term event, but then you get changes in the distribution of the species, or changes in the types of species that then thrive in that environment. And I think they refer to it as tropicalization. So you're getting these tropical species coming in, and they get quite comfortable, and they settle there because you've had this catastrophic event, and now the environment is more, it's nicer for them. Perhaps you know more about this, Emma. You want to comment there?
No, that's a perfect explanation, actually. I'm a marine scientist, for those of you who are listening and don't know my own research area, and we are seeing substantial changes in marine environments as a result of this average change in conditions, which is allowing species to move, but then sudden extreme events that cause massive die-offs of the habitat-forming species. They allow a phase shift in the community, which sometimes never reverts. And so I guess the interesting thing to refer back to the physical sciences now is, are we seeing these events happening more frequently? And of course, we're only starting to understand what extreme events are and what those long-term series are. But Andy, can I throw to you, are we seeing extreme events happening on a more frequent basis across the globe?
Oh, you do ask the interesting questions. It depends.
Mm-hmm.
So, temperature-related extreme events, no question. There is a quite remarkable and rapid emergence of heat waves, both in terms of their frequency, their magnitude, and their duration, emerging in very many parts of the world, no questions asked. In terms of something like drought, there are regions where drought clearly is becoming worse, but there are also regions where drought is becoming less of a problem. In things like rain, at least over Australia, the evidence would seem to be maybe slight reductions in the risk of average extremes, which sounds a contradiction in terms, but I'm just going to go with it for a minute. But when you move further and further to more and more extreme events in terms of rainfall, those seem to be becoming more intense, and that's from measurements. So you've got to imagine less events, but when they do occur, they're more severe. That's sort of what we think might be happening with tropical cyclones as well, slightly less common, but slightly more severe. We have no real knowledge of what's happening to other things like hail. The evidence around changing winds and extreme winds, virtually no evidence, one way or another. So it all depends where you are and what extreme you're talking about, which means that if you're really interested in extremes, and we should be, because they tip systems to become quite different, both in the marine and the terrestrial systems. They kill things. Lots of our ecosystems are able to withstand a certain level of a climate extreme, but go a little bit warmer or a little bit drier, and you kill important ecosystems. So these things are really important, but we have to get down into the granularity of where they're occurring to understand both the mechanisms and whether they are actually becoming more common or not. There is a good evidence on the internet of climate extremes becoming much commoner, but a lot of that is related to further human development, better observations, more settlement, a lot more vulnerability in Australia because we've done things like build houses on floodplains, and then we're really surprised when they flood. We've built vulnerability into many of our human systems, and we're now experiencing the consequence of that without actually necessarily changing the frequency of extremes. That's not to say extremes aren't becoming more frequent in some parts of Australia. Heat waves, undoubtedly.
So that's really interesting. And obviously we have an enormous continent to be talking about here. So you would expect climate extremes and climate in general to be reacting very differently in different parts of the continent. If we were to be most concerned about a heat extreme, I'm guessing that the biggest problem for humans would be around that dew point in the tropics, making places relatively uninhabitable when you get very high humidity and high temperature. What do we know about humidity and how that's changing under climate?
So we do know there are trends in humidity. If you translate all of the drivers of human comfort, there is good evidence in parts of Australia that the habitats are becoming less comfortable for us. We may not feel it because we live indoors or in air-conditioned comfort, but it is getting worse in some parts of the country. The really interesting, it's not, the tropics are vulnerable to this, and there is some work done by, for instance, Steve Sherwood at UNSW showing how long it will take before areas of the tropics are uninhabitable. But you also see this trend in southern Australia, Southeast Australia, where there's big enough change for people to really find it miserably uncomfortable as heat waves become very much longer. So this isn't something you can ignore if you don't live in the tropics. It matters to people wherever they live, particularly in our major cities.
And some of the compound events that we're seeing happening, Nina, and I'm thinking in particular, most people will have in their minds the massive bushfires. My understanding is that, yes, they were unprecedented in scale, but they also followed an unprecedentedly dry year, which affected the fuel availability, etc. Can you tell me, are compound events becoming more frequent, or we just really don't have enough data to tell what's going on?
For current climates, we don't really have enough data to speak to that. So I would say reliable data is, again, as Moninya pointed out, from satellite times. If we look into the future, though, so it's in our current work, we're using climate models to predict what's going to happen depending on different emission scenarios into the future. We do see that there's an increase in the occurrence of dry and heat extremes, so heat waves and drought into the future. So and that's actually quite significant. So by the end of the next century, it's 95% of the world population will see a doubling in the occurrence of days with heat wave and drought. And with drought and heat being two of the very important drivers of bushfires, this speaks to, well, it's very likely that we will see more of this. Of course, heat and drought is not the only thing that contributes to bushfires, but it's framing the conditions. And these conditions are more and more favoring bushfire conditions.
So that speaks to how extreme events will change into the future and how urgent it is that we act on reducing carbon emissions right now. Moninya, do we have a sense of how climate extremes in marine environments will change into the future? What are those predictions telling us?
First, if we look at what's happened over the past century, we see that globally, marine heat waves have increased in frequency by about 30% and increased in duration by about 17% over the last century or so. Along the east coast of Australia, which is my area, what we're seeing is actually they're moving. So these warm extremes are moving further south. And so we say that the southern coast of New South Wales is a hotspot of ocean warming. It really is one of the most impacted areas of the whole of Australia's coastal oceans. So you might think, so the water flows from Brisbane to Sydney to Eden to Tasmania along the east coast. And you might think that Brisbane, because it's the tropics, it's getting warmer, but it's not getting warmer as fast as what's happening off southern New South Wales, because these warm waters have never penetrated that far before, that far south. And so that's really sort of like this tipping point, or this shoulder region where the warm water is penetrating further south. So that's where we're seeing more marine heat waves and bigger volumes of warm water hanging around off southern New South Wales.
Moninya, tell me a little bit more about the whole idea of a hotspot, because I think a lot of people hearing and reading about climate change will be reading about average temperature changes across the globe. What do you mean when you say New South Wales waters are a hotspot of climate change?
A lot of that, the answer to that question comes down to resolution. So climate models are generally large space and time scales. So they might make averages over 50 kilometres and 10 years, or hundreds of years, trying to project into the future. My work is very much on the kilometre scale and weeks to months. And so at that scale, we're actually able to see the difference between an increase along the entire east coast and narrow it right down to a 100 kilometre square area, for example. And the models resolve the physics very well at that resolution. Excuse me. And so, so we can see that this particular region is warming faster than other regions. We can get that spatial resolution that's required to say more than the east coast is warming. The current that flows along the east coast of Australia is what we call a western boundary current, and there are 5 western boundary currents globally, and the western boundary current regions are warming faster than anywhere else on Earth, so 2 to 3 times the global average. But if you think of like a stock market trend and the uptrend, so you've got this mean trend, but then you have the extremes, highs and lows on top of that, which means everything's getting higher, so the extremes are getting higher, backed by that mean trend.
So that's a really big issue for local industry. I'll get on to impacts on people and industry in a minute and how we can build resilience, but I'm just going to throw to Andy for a little bit more about climate hotspots on land. I was reading that, the Arctic is getting up to 38 degrees in temperature. What do we know about where the hotspots are terrestrially?
You could go into an analysis of the climate models to tease out from the climate models where the hotspots are. But I think the truth of the matter is that's quite challenging and uncertain science for the reasons that Moninya just hinted at. The climate models are relatively coarse resolution, and a lot of the really big impacts are the nuancing of weather in the atmosphere or ocean currents in the ocean that gives you the detail of how things are changing. So we think we know where the hotspots are globally in terms of the large-scale changes in the climate, but those can be dramatically influenced by weather. And I'll give you an example. Australia slaughtered the temperature records for some New South Wales towns a couple of years ago, not because of the increase in CO2 above that town, but because the synoptic patterns changed, and those lovely southerly breezes that swept away heat waves and gave you a few days of respite from a heat wave didn't penetrate far enough to wipe away the heat wave. So instead of getting a few days of heat wave and then a cool change and a few days of heat wave, you just got a heat wave continuing right the way through the summer. If you think about that almost anywhere in the world, you get a situation where you get a warming trend due to CO2, but then the weather patterns are perturbed by that warming trend, and sometimes they might ameliorate the warming trend, and sometimes they dramatically escalate it. And where those things occur is very difficult to tease out from the coarse resolution climate models, or very impossible, which is why we're trying to drive the technology around climate modeling to the next generation to get to where Moninya is working, that scale that she's working at, but globally, which would be really cool.
It's all about bringing the global models and the local observations and the local model together. What kind of infrastructure do we need from a computing sense to be able to do that? Is it just a gazillion million supercomputers? What are we talking?
Exascale.
Exascale,
which is quite big. We have nothing like that in Australia at the moment. There's a couple of exascale computers being built around the world for various purposes. There's a big initiative that was announced a couple of days ago by the Royal Society to get us on pathways to exascale. It's around $1 billion a year, which is infinitesimal, I would like to say, relative to the money that goes into physics and gravity wave detection and CERN and Giant Magellan telescopes and all this really cool kit. We just need 1% of that funding to let you know what will happen at kilometre scale under climate change into the future. which seems like a really good investment to me.
Well, yeah, and it's interesting, even pitching it against other investments in science and technology is an interesting contrast, but pitching that against the cost of natural disasters when they take place, then you really start to see how important it is that we invest in understanding where these disasters are going to take place and investing in the resilience. Now, Australia has been very active in the last year or so, in large part in response to the bushfire disaster, in trying to understand how we build social resilience and build our systems and our communications, and a lot of investment is going into that. Are we seeing enough investment in understanding the underpinning science of extreme events, Andy?
So, what do you need to adapt to? If you build a dam for water supply and it never fills, it was a waste of money. If, however, you don't build a dam and that catchment becomes much more flood prone because of severe rainfall, you've missed the opportunity to protect a system. So you can't strategically invest your adaptation dollar without first having an awareness of what you need to adapt to. So in Moninya's world of ocean resources and fisheries, we can probably adapt to some of the changes she's talking about, some of them, if we have good understanding based upon the observations and the modeling of what's going to happen. But it's really hard to adapt to stuff that you don't know is coming. And in order to know what's coming, you have to invest in the data and the modeling to give you a heads up of what you need to adapt to. And around the world, the investment in those things which are to protect people from disasters has, in my view, not been remotely sufficient to give us a good chance of avoiding the worst case scenarios.
So Moninya, just throwing to you, as Andy was saying, are the local models that you have, the East Australian Current, for example, and that the 30-year data set or the 70-year data set, are they enough to allow you to make useful predictions, say, to help fisheries respond to climate change or extreme events?
If we step back to the question Andy answered before about the magnitude of the effort that's required, I would say we need more observations. We need more observations to ground truth and validate our models, and to know that our models are doing the right thing and that they're statistically they're accurate and can give us that picture. Can we make predictions about the future now? Yes, we can. But knowing what the errors on them are is very important. And so that's where people get into multiple models and ensembles, and that real statistical approach to the results. Just having one projection is not enough. But on the scales that we work at, having a very high resolution model needs to have very high resolution data to assimilate into it to make the model, better. And we're still learning how to do that. When you're studying at the broad scale and you have average observations and an average result, it's actually easier. The physics and the assimilation of that data is easier. But when you get down to the very fine scale and you're down to submesoscale physics, it's far more challenging, and the changes happen far more quickly, which means you need more data.
Moninya, you're sitting in a department of maths and stats for a reason, and you just explained that really well. A lot of it is about getting multiple models working together. You talked about ensembles of models, but you're also very practical and out on the ocean yourself, and your teams are. Can you just describe for those listening in some of the new bits of kit that you're using to get those observations subsurface? Because I don't think many people would have seen the bits of gear that you fly around the ocean.
We have some great tools, and thank you for asking that question. One of the main ones is what we call an ocean glider. And these gliders, they look like little torpedoes or mini submarines. They're only about 1.5 to 2 meters long and diameter of 15 to 20 centimeters. But they can fly out in the ocean for between 3 weeks and 3 months. And they profile from the surface down to 200 meters and then back up to the surface. And some of them go down to 1,000 meters. And they're collecting observations all the time. So they are one of the most useful pieces of kit we have, and they don't get seasick, right? They can go out and measure in the most extreme conditions. Part of the problem with understanding marine extremes and high impact events such as East Coast lows is that we can't observe them enough. We don't want to fly an aeroplane through an east coast low, or we don't want to be at sea in a ship when there's an east coast low event. You know how catastrophic they can be. But these little underwater robots can just measure continuously. And so we had one out during this last flooding event, the big rainfall event in March we had along the east coast of Australia. We were able to get a glider in the water, and it was measuring the changes that were happening in the ocean as all this fresh water flooded out from the coast into the sea. So that's one remarkable piece of kit. Another piece of kit we use is high frequency coastal radar, and they sit on land and they send out sound signals that actually measure the surface currents, and then we can get really broad spatial coverage. And that's another really neat tool for getting that broad coverage that then we can assimilate into our models. And they're two modern pieces of technology that we're using continuously now along the east coast of Australia to really try and get the data that's necessary to improve the quality of our models.
That's great to hear, and it reminds me of a modern piece of technology that's stuck to a very old animal called an elephant seal now as well, and we're using elephant seals to get that kind of oceanographic information under the ice in Antarctica, because of course very hard to get under there, but they're naturally beautiful divers and bringing back a lot of information. So there's lots of innovative ways to collect new data. Nina, can I ask, in your modelling of these brand new types of events, are you relying on new data sources, or are you relying on new mathematics and statistical approaches in order to try and make those predictions? And before, I'm going to give you a double-barreled question. I also want to know, what were the predictions for compound events in Australia? Are we really in trouble?
To answer the first part, so what I've been using so far, or what is normally used, is observations that we've had, that have been used for the univariate extremes as well. What is different, because compound events are a combination of different hazards, we need different tools. So we use different kinds of statistics. So instead of univariate statistics, we go to multivariate statistics. Very frightening name, it just means we are using a different type of tool, a different toolbox, to come to the same conclusions that we would for the univariate. So we can inform stakeholders and decision makers. To use second part of what does the future bring? So in our work, we have looked into different types of compound events. We looked into the co-occurrence of extreme precipitation and extreme winds, as well as drought and heat waves. So we chose those because they have caused very high impacts over the past decades. Heat waves and droughts have caused most of the fatalities over the world, and wind and precipitation, so storms, which are normally the drivers of these events, have caused the highest damages. So we used our climate models that we normally use to predict future changes in temperature, for example, and look to what do they tell us about the occurrence of these events. In Australia, as I said, globally, we already find an increase in the co-occurrence of heat waves and droughts. Same is for Australia. It's roughly the same frequency that we see, the frequent change that we see in Australia, like globally, so that's very homogeneous. For winds and precipitation, it is very dependent on the location where you are. So you see quite a bit of increase, or we see increases in the occurrence where we already see high occurrences, high frequencies of events, like in West Australia or Cairns area. But that is also very, the uncertainty is very high, because it's very hard for models to agree on changes in precipitation and winds. That is, again, something where we need more observations to tune our models, to train our models to do better in current climates, to get these features right. So,
again, very, very challenging, and a great scientific challenge. If it wasn't so desperately urgent and so problematic, it would be exciting. So yeah, and again, just reminding everyone listening, it's, the Australian continent is so broad and so vast, and And in some areas, rainfall's increasing on average, you know, in the northwest, I understand, and I'm not an expert in rainfall, but in other areas, it looks like it's drying out and or becoming different in terms of falling in different seasons. So the complications can get quite extreme. We're getting some interesting questions coming in from the audience. So I'm gonna throw to the first one here, which is actually from John Turnbull, so a UNSW research associate. He says, great discussion, thank you. So how far are we taking our models into the domain of human or social effects? And I think I'm going to include financial there as well, because I know some people are looking at that. And for example, John says, the well-being implications of compounding extreme events, would this be a way for us to raise the profile and attention on extreme events and perhaps even lead to increased funding? I'm going to throw to Andy first.
Thanks, Emma. There are many different modelling approaches to explore these sorts of issues. There are things called integrated assessment models, there's climate models, and there's many different kinds of models which are domain specific. All of those are being used and examined to try to understand the sorts of things we're talking about here, but there tends to be a disconnect. The work that Nina spoke of in terms of compound events, as she said, is very new. So if you go, for instance, to the economic models, they tend to look at the impact of temperature, not even temperature extremes. So if we look at, for instance, the new advice from APRA, they are saying to businesses they should look at their resilience to 4 degrees. The problem is there is no association between a 4-degree rise in the global temperature and any expression of compound events or extreme events at the scale a company might be vulnerable to. Those things don't link together. So we have to bridge those relationships. We have to bring the modeling that we do closer to what the financial sector or the ecological sector need. That's a huge undertaking. It's a decade of work to increase the spatial detail in a climate model from 100 by 100 to 50 by 50 kilometers. These are multi-million lines of computer code. You can't just do it. But we are trying to bring the work we do much closer to people who need the information we do, and we're working with some of those people to make sure the information we can already provide is used appropriately and not misused, which I'm afraid it can be in some sectors.
Very awkward, but also interesting because it points to the idea that we also need to use observations of social and economic impacts of extreme events, a bit like Moninya's been arguing around the need for more real observations in ocean environments. Perhaps because it is so difficult to predict into the future, we can learn from those events. And I'm sure that many people were studying the impacts, particularly insurance companies, of recent natural hazards. Are insurance companies one of the areas in which they have perhaps the closest understanding of potential impacts on financial and social activities as a result of climate extremes? Because you do see them starting to pull back from insuring, you know, houses in particular areas or putting a few extra clauses in their insurance guarantees.
The insurance industry is well informed and are very, very good at assessing risk. And because they reset their premiums, they're relatively able to withstand trends in extremes. But there is a considerable concern in that industry of reputational risk by removing themselves from certain markets. So there are strategies the insurance companies can do. The big one are the reinsurance companies, and perhaps much more significant than that, big organizations that have a focus on the next 10, 20, 30 years. Superannuation companies, for instance, where they can invest now, expecting a return in 20 or 30 years, but could be left with some really expensive stranded assets because the value of that asset is evaporated because of transitional risk associated with climate change. The other really interesting group of organizations getting really excited about climate extremes are the rating agencies. They rate risk, and they're beginning to, well, they are now utilizing climate change information to help them rate risk. And that has a huge implication because it affects the cost of capital. So you might not think you're vulnerable to climate change. You might be a business that doesn't care about climate change, but you suddenly find the interest rates on your capital have just gone up by 2% because Moody's think you are vulnerable. That's changing the landscape for climate change really extraordinarily quickly, because trillions of dollars are changing the way they flow through the global economy as a consequence of how climate risk is assessed.
And a lot of our response is limited by inertia. So developing agile systems of responding and making sure that they're being driven by the right information is going to be critical in the next few years. I've got another question from the audience, and I think, you know, it's a really interesting one. Moninya, you may be able to comment on it. I'm not sure, but I know that there are net negative emission technologies that are being considered for both land and marine. So does anyone know anything about these? We've got a question here. If today we would stop increasing carbon dioxide emissions and reach a peak in atmospheric CO2 concentrations, could we safely stay at this level, or would we continue to see environmental degradation? And do we need to look at ways to reduce the current carbon dioxide and atmospheric concentration? So I'm interpreting that as being, do we need net negative emission technologies such as ion fertilization of the ocean or pumping carbon dioxide into the deep earth? Any takers on this one?
Well, I can answer that to a degree. The whole point of net zero is not to create technologies that enable us to continue to emit 10 billion tons of CO2 a year and find some cool technological solution to remove 10 billion tons of carbon a year from the atmosphere. That's not the game. The game is to cut emissions to near zero real fast, and then that little bit of emissions that you can't get to zero, you have some strategies around soil carbon, revegetation. I hate ion fertilization because it's let's play experiments with the ocean because we've been experimenting with the atmosphere by emitting CO2. It's not a very, very smart strategy. Most of the attempts to generate negative emissions are almost certainly futile. The words almost certainly is really important there, because we can't be absolutely certain whether they will work or not, because most of the research has never been done to really evaluate them. But actually, we know how to get emissions to near zero. Why don't we do that first? Right? Not rocket science.
Good strategy. However, I understand some of the modelling suggests that we will need net negative emissions technologies even when we get it to zero, just because of the inertia in the system. And certainly the oceans show that, don't they, Moninya? Even if we got zero emissions now, the oceans would continue to heat up for hundreds of years. Is that right?
They are absorbing large amounts of heat. So I suspect that's probably right, Emma.
We have a specific question for you from the audience, and it's really, how do marine heat waves affect fish and animals?
Yeah, that's a good question. It depends on if the animal can move or not. So, you know, if you're an animal in the ocean that's stuck to the bottom, a sessile organism, and you can't move, you're going to be far more affected than an animal that can move. And if you're an animal that can move a long distance. A few years ago, there was a very big marine heat wave in the Tasman Sea, and the New Zealand hoki fishery got hit quite badly. That's a deep sea fishery down at about 1,000 metres depth. We had no data to show what that temperature extreme was, or that anomaly was down that deep. I think I found 2 data points in that entire marine heatwave event at 1,000 metres. But what we saw was a very big cut, or a financial hit to the fishery, due to the fact that they were not catching their fish. And that allowed the fishery got together, the hoki fishery got together and took a voluntary quota cut as a response to that, while they figured out what was going on. Because they didn't know if the fish had swum away, gone somewhere else, or if the fish just weren't there. They just, you know, there were no fish. And we're still just starting to put it all together. We're trying to collect the data. So what we're actually doing is instrumenting fishing vessels now with temperature sensors, so that we get those fishing profiles, those deep temperature profiles, every time a net gets cast. And it's a really great way to tap into citizen science and crowdsourcing oceanographic data, we can also give the seafood sector that information they need to try and correlate their catch with the temperature in the ocean. So that's a new initiative that we're working on right now.
And again, speaking to the need for agile management systems, if people are going to have to move fisheries, entire fisheries, in order to respond to the movement of these mobile organisms that are choosing a different habitat because of a temperature change, then all of our sort of spatial management approaches are going to have to become quite flexible. That's another interesting challenge for ecological managers. Back to what you're just mentioning there, Moninya, on citizen science. We had another question from an audience before the session, and it really speaks to are there great methods or case studies of student engagement or citizen science engagement that would help people understand extreme events? You got any examples where people are jumping in the ocean, taking temperatures for you, or what's happening?
People are trying to do it in all sorts of areas. So we've got an example coming out of the United States where they're putting temperature sensors on surfboard fins. There's a group in Spain that are putting temperature sensors on scuba diving tanks. As I said, the Australians and the New Zealanders are trying to put sensors on every fishing net and pot and line that goes out in the ocean, trying to use these platforms as platforms of opportunity. Another example close to home, which some of you might be familiar with, is the Coastal Snap initiative run out of the Water Research Lab from UNSW, where they've put up little camera mounts, cell phone camera mounts at a whole bunch of beaches. So any passerby can take a little photo, position their cell phone in that camera mount so it's lined up exactly, take a photo of the beach and upload it to social media with a hashtag. And all those photographs then get collated. And with that, they can look at shoreline change. They can look at how the beaches are moving, particularly after extreme events. So you get this big East Coast low event or a big storm event and a whole bunch of sand gets removed, and you get all the locals coming out and having a look at it and taking their photos. So it's a really great initiative, and they've got thousands of photos now from that, which people are doing really good science on.
Yeah, that's a great idea to actually just put the frame there so that you don't get the camera stolen. People bring their own camera, line it up. An excellent initiative. I've seen some great shots from Coast Snap actually on Twitter, and you can see really substantial changes in shorelines in response to extreme events like our East Coast lows, which are the subject of a lot of study and concern in New South Wales. The Centre for Excellence in Climate Extremes has also developed some material for classrooms and is willing to work with teachers. Nina or Andy, would you like to speak a little bit to those resources?
So I better do that because I think Nina's been focusing on her research.
Outrageous.
I know. I don't know what I pay her for. Oh, yes, doing the research. We have been developing some particular resources, particularly for high school students. We've been doing this in liaison with high school teachers. We're very conscious that science teachers don't have free rein on only teaching about climate extremes, which would be terrific if they did. So we've been creating modules in dialogue with some high school teachers, which help communicate some of this stuff to kids. In particular, we're trying to get through the message that if you want to come and work in this area, you've got to be quantitative. You have to have done math. You really like to have done physics or chemistry or computer science, not just understand the issues, but be able to diagnose problems with what we do or build software that helps us describe data or move forward in the modeling. So we're trying to both provide useful information to teachers, but also to communicate to the kids the sorts of things that high school education feeds into a proper science degree at a university. So those materials, I think, are fairly freely available, and I think we might have some information where people listening to this could get further information on that if they wanted.
Yeah, so in the chat function, if you're listening in and you are interested in engaging with some of these teaching resources, there'll be a PDF upload or a link to a PDF, which you can then see some of those resources, the websites and what's on offer. And there's a workshop coming up on the 28th of July, actually, a workshop for maths and STEM teachers. It's completely free, and that'll help you develop some of these climate extreme materials in line with your curriculum, so that you're not actually taking away from all of the other material that you need to teach. And we know that we've got a packed curriculum. Andy, I'm really pleased to hear you shout out the whole importance of doing quantitative studies, but I also want to make sure that people understand these days you can do your arts and your languages and your musics and your social sciences as well as the maths and stats. In fact, we welcome people doing double degrees these days, and that's a way of making sure that you've got all the skills you'll need to tackle these, or to help tackle these grand challenges that we've been speaking about today.
If I could just comment there, Emma, I
Yeah.
used to, when talking to high schools, I used to sort of have a line that almost anything that you studied was relevant to helping with the climate change problem. And I think I said something like, except maybe music.
What's
and afterwards, somebody came up to me to showcase an amazing piece of work they'd been doing, helping communicate climate change through music. So I can't even exclude anything anymore, because every area of study can be aligned to helping solve the climate change problem. There is nothing excluded from that.
That's absolutely right. And what we've been able to feature today, thank you very much to all the panelists, is some of the cutting edge research that's going on in understanding essentially new phenomena. Now, we started by talking about Australia as being a land of extremes, not shy of dealing with extremes, because the whole environment has evolved in response to extremes. But what we're talking about now, and what you've heard about today, is the very beginning of understanding extreme extremes. And so this is where we move into a world that we don't really yet understand. We don't understand yet when compound events will take place, when they might be consecutive, when events might actually mitigate the impact of each other because they take place together. We're starting to understand movements of warm water in the ocean and how that might affect the biota there. We're also starting to see, shockingly, very large ecosystem shifts around Australia. So up to 40% of Australia's coastline has been impacted by extreme events. The coastal habitats have been impacted by extreme events in the last decade. So something very, very serious for us all to be thinking about, not only for the animals and the plants out there, but also for our businesses, our livelihoods, our homes, and our social activities, which everyone knows have been severely impacted by climate extremes just recently during the bushfires. It's been an absolute pleasure to showcase some of our expertise at UNSW. We are always welcoming people in, not only STEM teachers, but undergraduates and students. And we like to run a lot of these public events to help communicate the science that we're doing on an everyday occasion. So on behalf of UNSW Science, thanks to our panellists, Professor Andy Pitman, Professor Moninya Roughen, and Dr. Nina Ritter. And I've pigeonholed you all into your areas of expertise, so forgive me, but I know you have very broad areas of expertise, and we'll get you back for another chat later. Thanks to everyone who tuned in for the live discussion, and to those of you who contributed questions both during the chat and also prior to the chat. I incorporated many of them into the questions that I was asking our panellists today, so thanks very much. It's a very engaged event. It's been interesting. It's been somewhat scary. Please leave with some optimism. There is a lot you can do to reverse climate change, but we just need to do it very, very quickly. If you have found today's event interesting, we're actually going to be chatting more about extreme events, but with a special focus on bushfires, and some of our other experts at the University of New South Wales on bushfires, modelling bushfires and the impacts of bushfires. That event will be on the 8th of July, and we'll be discussing the ongoing threats, but also resilience. The details of that event will actually be posted today to everyone who registered for this event as well. So you'll see that coming up soon. And finally, if you have a spare few minutes now, there will be a link to a feedback. So it's just a really short survey to say how the event went, what worked, what didn't for you. We really appreciate any feedback, and it helps us build the Sci-Fi event series as we go. We hope you enjoyed the session. Thanks again for joining us.